Hello, in this lecture, I'll be starting Unit 3, which deals with special functions and differential equations as per the syllabus prescribed by MG University, Kotte. In this unit, we will be coming across some special functions as well as differential equations which are of great use in physics and which find their place in various problems in physics. First of all, we'll be seeing what gamma function is. Gamma function is also called factorial function, and this was proposed by Euler to find factorial for non-integer values. We all know that factorial can be defined like this: n factorial, n into n minus 1 into etc. 3 into 2 into 1 for n greater than 0, and by definition 0 factorial is given as 1. Double factorial can be defined as n into n minus 2 into n minus 4 into etc. It terminates at 1 if n is odd, and it terminates at 2 if n is even. Now, how do we connect single factorial and double factorial? Single factorial is related to double factorial as n double factorial into n minus 1 double factorial. You can just check it for yourselves because n double factorial doesn't include the term n minus 1 into n minus 3 into etc. So in order to include those terms, you will need such a double factorial. So if you take a product of both these, you're likely to end up with n factorial. Factorial function can also be defined in different ways. One way to define factorial function would be to take product of all numbers k, where k goes from 1 to n. So the instruction given by this is you put different values for k starting with 1 and ending with k, and you take product of all those things. So that is of course n factorial. The second way to define n factorial would be to take the nth derivative of x raised to n. This is very simple to understand. Suppose you have a function x square and you are asked to take second derivative of x square. What would be the first derivative of x square? It would be 2x, right? So if you take a derivative once more, second derivative means taking derivative of 2x. So you end up with 2 into 1, right? So what is 2 into 1? It is 2 factorial. So when you took the second derivative of x square, you ended up with 2 factorial. So what would you get if you take nth derivative of x raised to n? You would obviously get n into n minus 1 into etc. up to 1. That is n factorial. So another way to define n factorial would be nth derivative of x raised to n. In order to include non-integer arguments, Euler proposed an integral representation for factorial, which he gave as z factorial is integral 0 to infinity t raised to z e raised to minus t dt, with a condition that z should not take values minus 1, minus 2, minus 3, minus 4, etc. For all these values, this integral will diverge, but it is defined for all other values. So let's see. Now, gamma function, gamma of z, is defined as integral 0 to infinity t raised to z minus 1 e raised to minus t dt. Just before we saw that z factorial was defined as t raised to z e raised to minus t dt within the integral from 0 to infinity. Therefore, this integral 0 to infinity t raised to z minus 1 e raised to minus t dt would obviously be z minus 1 factorial. Now let's see what we get when we integrate this integral. So you take e raised to minus t as the first function, you integrate the second. When you integrate t raised to z minus 1, you get t raised to z minus 1 plus 1 divided by z minus 1 plus 1. That's what we have, t raised to z by z. All this within the limits 0 to infinity. And then minus of integral of derivative of your first function. Your first function was e raised to minus t. When you take the derivative, you will get minus of e raised to minus t. So that becomes a plus, and you have integral 0 to infinity e raised to minus t. Then again integral of second. Integral of second we saw just before, t raised to z by z dt. See, when you consider this first term, this becomes 0 under both limits. When you take the upper limit, you have e raised to minus infinity, that's 0. And when you take the second term, there is a t. So when you apply the lower limit, that becomes 0. So your first term vanishes under both limits. So you're left with a second term which involves another integral. Now this is an integral in t. So it's not a problem if you take this z outside the integral. So you just have 1 by z 0 to infinity e raised to minus t raised to z dt. Okay, you take this 1 by z outside the integral. So you have an integral e raised to minus t raised to z dt. Now, just before we saw that this integral was z factorial, right? Now, by definition, t raised to z minus 1 e raised to minus t dt is z minus 1 factorial, and that is what is defined as gamma of z. So what would be z factorial? It would just be gamma of z plus 1, right? So this integral is gamma of z plus 1. Or in other words, this integral is z factorial, and z factorial is gamma of z plus 1. So you started with what? You started with this thing, gamma of z, and you have 1 by z times gamma of z plus 1. So just rearranging the terms, you have gamma of z plus 1 is z gamma z. This is a very important relation. So you have the value of gamma z, you can compute any other uh, factorial values. So let's see what are the values when of gamma of z when z equal to 1. When z equal to 1, you have gamma of 1. Gamma of 1, instead of z you just plug in 1. So your integral becomes like this, and when you integrate this, you end up with a 1. You take gamma of 2. By definition, your gamma of z is integral 0 to infinity e raised to minus t raised to z minus 1 dt. So that's what we have done here. You integrate this, you apply the limits, you end up with a 1. Gamma of 3 you can compute in the same way. You can do the integration. Just check for yourselves. You will end up with a 2. So we have a relation connecting gamma of z and gamma of z plus 1 as gamma of z is gamma z plus 1 by z. So when z equal to 0, when z equal to 0, you have gamma of 0, and gamma of 0 is not defined. Gamma of 0 is gamma of 1 by 0, which is not defined. So since gamma of 0 is not defined, by this relation, gamma of z is gamma of z plus 1 by z, or the other way around, gamma of z plus 1 is z gamma z. Since gamma of 0 is not defined, gamma of minus 1 is not defined, gamma of minus 2 is not defined, all these are not defined. All these are infinity. Another definition of gamma function, this is not an integral representation. We just saw the integral representation proposed by Euler. This is another way of defining gamma function, and this is called the infinite limit form. We can just understand it by looking at the representation itself, why it is called the infinite limit form. So gamma of z can be defined as limit n tends to infinity, and you have a fraction over here where the numerator includes 1 into 2 into 3 into etc. up to n, and the denominator has terms like z into z plus 1 into etc. up to z plus n, and then you have n raised to z. Here again, z cannot take the values 0, minus 1, minus 2, etc. minus n. This is quite clear from this representation, because for all these values, this function just blows up. So now let's see, if this is gamma z, then what would be gamma of z plus 1? So instead of all z, you just write z plus 1. So this term would be z plus 1, this term would be z plus 2, and this term would be z plus n plus 1. And here this n raised to z, this would just be n raised to z plus 1. So you see that both these definitions, they have a lot of terms in common. So let us just segregate all those terms. 1 into 2 into 3 into etc. up to n, that is common. And for gamma of z, you had a z in the denominator, and your terms in the denominator terminated at z plus n. Whereas for this thing, your terms starts with z plus 1 and it terminates at z plus n plus 1. So there is one thing extra over here, but one term is missing. So what is the missing term? Z is missing, right? So just think of multiplying and dividing with a z. So what do you get? And here you have an extra term. Here it was just n raised to z. Now you have an n raised to z plus 1. So just write it separate, n into n raised to z. Just write it like that. So then what do we have here? When you do all that, you multiply with a z in the numerator and denominator. You segregate this extra term. Then you write this n raised to z plus 1 as just n raised to z into n. Now you write all those extra terms separate. So here you have 1 into 2 into 3 into etc. up to n, and the denominator you have terms starting with z and ending with z plus n, and then an n raised to z. Then this fraction, this is extra, nz by z plus n plus 1. Okay. Now what is this portion? This entire portion is gamma of z, and plus you have some additional terms. So when you have such a fraction, don't just directly apply n tends to infinity, because again you will end up with an indeterminate form. Infinity by infinity, you will get like that if you apply the limits directly. So divide with an n and then you apply the limits. When you divide with an n, you have z in the numerator, and when you divide with an n, you have such terms in the denominator. So now when you apply the limits n tends to infinity, this term becomes 0, z by infinity, that becomes 0, 1 by infinity, that also becomes 0, and then you end up with a 1. So you have a limit n tends to infinity, z divided by these set of terms, you end up with just a z. Okay, so as n tends to infinity, your RHS becomes z gamma z. So what was on your left hand side? Left hand side was gamma z plus 1, and on your RHS you have z gamma z. This we proved just before with the integral representation also. So this is another proof for the fact that This is also a representation for gamma function, because using this definition also you arrive at the relation connecting gamma z and gamma z plus 1. Another representation for gamma function is called the infinite product form or Weierstrass form, where you define gamma of z like this: 1 by gamma z equal to z e raised to small gamma z product of 1 plus z by n e raised to minus z by n, where n goes from 1 to infinity. This small gamma is a constant which is called Euler-Mascheroni constant, and it takes the recurring decimal value as given here. This form also can be derived from the infinite limit form. You may just refer to your textbook for study, Mathematical Methods for Physicists by George B. Afkin, to get more details about this form. That is an assignment for you. In various problems in physics, gamma function may appear differently. Not always gamma function appears like this: integral 0 to infinity t raised to z minus 1 e raised to minus t dt. It's not like this that gamma function appears in all problems in physics. Sometimes it may take different forms. So we should understand that this is gamma function. Just consider that you are taking t as y square. So your dt becomes 2y dy. Your limit doesn't change, it remains 0 to infinity. But when you have this variable change, you see how your integral changes. Instead of t, just plug in y square, and here you have an e raised to minus y square, and instead of dt you have 2y dy. So with this your integral becomes like this: twice integral 0 to infinity e raised to minus y square y raised to 2z minus 1 dy. This is also gamma of z. Okay, so when you encounter such integrals, you should understand that this is also gamma function. Similarly, instead of this t equal to y square, if you had put e raised to minus t as y, then your t would be, you take log, you get log 1 by y as t, and your dt becomes y times minus 1 by y square dy. Okay, and you end up with a minus 1 by y dy for dt. When you do all this substitution, okay, here the limit will also be different. As t goes to 0, y goes to 1. See, here you have substituted y as e raised to minus t. So when t is 0, you have e raised to 0 and your y becomes 1. And when t goes to infinity, you have e raised to minus infinity, which is 0. So when your t goes to 0, y becomes 1, and when your t goes to infinity, y becomes 0. So your limit changes like this. Gamma of z becomes 1 to 0. The integration limits become like this, and your substitution goes here, and gamma of z can also be defined like this. See, you have a minus sign here, so you can just interchange the limits and make the integral a positive one. So you have 0 to 1 log 1 by y raised to z minus 1 dy. That is also another form for gamma function. Now let's just find out gamma functions for certain values of z. You have gamma of half. If you want to know the value of gamma of half, you just take this form of gamma function that we saw just before. You plug in the value z equal to half. You end up with such an integral. This is a standard integral. whose value is root pi by 2. So you have gamma of half as root pi. Again, that is an assignment for you, how to evaluate this standard integral and to find out its value. You can just do it for yourselves. Find it out how this standard integral takes the value root pi by 2. Now gamma of 3 by 2. We know that gamma function satisfies the relation gamma z plus 1 is z gamma z. You know the value of gamma of half. How can you write 3 by 2? 3 by 2 can be written as 1 plus half. So gamma of 1 plus half, or in other words gamma 3 by 2, would be half gamma half. You just saw that gamma of half is root pi. So your gamma 3 by 2 would be half root pi. Gamma 5 by 2 would be 3 by 2 gamma 3 by 2. You will have 3 by 2 times this value, half root pi. So in this way you can define gamma n plus half like this. So by knowing just one value, knowing one gamma z, it's possible to compute all the other values because gamma function satisfies such a relation. This is a graph where you have you can see the different values of gamma function for real values of x. So you can see that the values diverge at certain specific locations. You can see it diverges for -1, it diverges for -2, -3, -4. For all these values, the value of gamma function just goes to infinity. For all these values, -1, -2, -3, etc. Only at those specific locations the function diverges. There are certain very important relations that gamma function satisfies. One such a relation is called a Legendre duplication formula, which is given like this: 2 raised to 2z minus 1 gamma z plus half is root pi gamma 2z. Or in it can be put in a different fashion, this relation: gamma z plus 1 into gamma z plus half is 2 raised to minus 2z root pi gamma 2z plus 1. This is Legendre duplication formula. We have an elaborate proof for this formula, which we will be seeing when we see beta function. Another relation that gamma function satisfies is called reflection formula, where gamma z into gamma 1 minus z is pi by sine pi z. You can of course use this relation to compute the value of gamma of half. When you plug in the value z equal to half, you have on your left hand side gamma half into gamma half equal to pi divided by sine pi by 2. Sine pi by 2 is 1, and you have gamma half square as pi. So your gamma half would be root of pi. Using this reflection formula, you can find out several factorial functions and their connections. So when you plug in z equal to 1 by 3, you get gamma 1 by 3, gamma 2 by 3 is 2 pi by root 3. Just do it for yourselves. It's quite easy. Now let's see a problem using gamma function. Suppose you have an integral e raised to minus x cube dx. You can solve this in different ways. You might already have learned several ways to solve such integrals during your plus 2. We will now solve it using gamma function. For that, initially just make a substitution t equal to x cube. Now when you put t equal to x cube, your x can be written as t raised to 1 by 3. Then your dx becomes 1 by 3 t raised to 1 by 3 minus 1 dt. So you totally change the variables from x to t. Then your integral looks like this. See, you take this 1 by 3 outside. So you have, what do you have with yourself? 1 by 3 integral 0 to infinity e raised to minus t raised to minus 2 by 3 dt. You just consider this integral, this um, and you consider the form of gamma function that we saw just before. This resembles this integral, isn't it? So uh, here you have e raised to minus z t raised to z minus 1 dt, and here you have e raised to minus t. Uh, okay, sorry, here it is. I have made a mistake over here. It is e raised to minus t, e raised to minus t, t raised to z minus 1 dt. We had seen such a form for gamma function, and comparing with that form, you can understand that instead of z minus 1, I have here 2 by minus 2 by 3, right? So, so instead of z minus 1, I have minus 2 by 3. So my z becomes 1 by 3. So what does this integral represent? This integral represents gamma function, gamma of z, right? So what would this integral represent? This integral would represent gamma of 1 by 3. I hope it is clear. Just compare this integral with this one. You can see that here you have e raised to minus t, that's there. And instead of t raised to z minus 1, you have minus 2 by 3 in place of z minus 1. So from z minus 1 equal to minus 2 by 3, you can find out what is the value of z. So if this integral is gamma of z, then this integral would definitely be gamma of z for that particular value of z which you evaluate from here. Now what is that particular value of z which you evaluate? It is 1 minus 2 by 3 and it is 1 by 3. So this integral is nothing but gamma 1 by 3. You just saw before, right? What is gamma 1 by 3 related to? So this integral is gamma 1 by 3. This integral is gamma 1 by 3, but just remember we had taken a 1 by 3 outside. So the question was integral 0 to infinity e raised to minus x cube dx, which would be 1 by 3 times this integral. This integral is gamma 1 by 3, so your answer is 1 by 3 gamma 1 by 3. Just evaluate and see for yourselves and show that integral 0 to infinity e raised to minus x raised to 4 dx is gamma of 5 by 4. Just follow the same method. Give a change of variables, then you will arrive at the answer. I hope this session on gamma function was clear to all of you. Just go through your textbook to find your reference book or other reference books to find out other problems also on this topic. Thank you.